the standard. And then during the last class, we were just trying to see like what are the shortcomings of the standard model, and these are actually collectively all these shortcomings, they collectively offer you the motivation to go or to probe beyond the standard model. So this is where we stopped yesterday during the last class on the 18th. So I will continue from here. So we have already seen the context of the neutrinos, because the massive neutrino is one of the shortcomings of the standard model. To be rather precise, the existence of the massive neutrinos till date is the only experimentally verified reason or the phenomenon which is a confirmed motivation to go beyond the standard model. But as we will see during the course of today's lecture, that there are more. So to start with, I will now consider the next thing, that is the dark matter. So if you just consider the velocity distribution for the galaxy, starting from the center, if you go too far away, so there is a verified distribution law according to the laws of the Kepler, and there is something known as the Keplerian decline or Keplerian fall off, which you can easily derive if you actually start from the virial theorem. So that is given by the calculated or the theoretical expectation. So the initial part is the point mass, then you have the star mass, which actually falls off if you go to the large distance. So this is very well done, you can verify it rather easily. But it turns out when they measure the galaxy rotation curve experimentally, it turns out that initially there is just like a point particle, like everything is concentrated at the center, there is a distribution like that, but then instead of having a fall, it actually shows some kind of constant plateau-like behavior. So this is not understood. One of the possible explanation of this observation is that, okay, there are some things which are like non-luminous matter, and maybe they're interacting in a different way. So that is what we don't see them the way we used to see like planet and galaxies and other things. So maybe that is the reason. And those non-luminous matters are collectively known as the dark matter. Now, there is a word of caution that there are several explanations about this particular incidence, but in the context of the particle physics, we consider the particle dark matter. So we would like to look for some DSM particle which may act like a dark matter, that is stable. They are not decaying. Although to be very precise, if you are having a reasonable I'm sorry, but I see some lines on my screen. This is something that
yes.
I'm not.
Yes, you have some lines on your screen, but I think it will be okay.
Yeah, but this is something I'm not doing. I don't know why these are, why it appears all of a sudden.
Just carry on.
Okay. Yeah, so this is some Galaxy 7 next. I don't know who is that student, so please don't do that. So this is something, it requires an explanation beyond the standard model. Of course, in the context of standard model, often people believe that there is something known as the action. There is a possible origin for that, but I'm not going to get into that detail, so that you can see.
Sir, Pradipta sir.
Yes.
Please, 1 minute. I'm sorry to interrupt with you. আমি ডিপার্টমেন্টের ডক্টর নন্দী, একটু ওদের প্রদীপ্ত জয়দীপদের সঙ্গে চেয়ে একটু সিনিয়র। আমি সুশোভনকে রিকোয়েস্ট করব, সুশোভন তুমি দেখো তো এটা ট্র্যাক করতে পারো কিনা, হু ইজ ডুইং দিস সাচ টাইপ অফ থিংস ইন বিটুইন লেকচার। সুশোভন, I request you. Sushobhan is there. Joyita? Hello?
হ্যাঁ, সুশোভন আছে স্যার।
ওকে একবার দেখতে বলো তো ট্র্যাক করতে পারে কিনা, এটা মানে চেষ্টা করে দেখুক অন্তত যদি পারে।
করছে কি জানি, বুঝতে পারছি না, দেখছি।
আচ্ছা ঠিক আছে, সরি ফর ইন্টারাপ্টিং ইউ। প্লিজ স্যার কন্টিনিউ, প্লিজ স্যার কন্টিনিউ।
Okay, sir. So there is a belief that action may be a candidate for the dark matter even inside the standard model, but there are certain properties which we know about the dark matter. So you will see that actions by themselves, they cannot satisfy all the measured properties or the properties that you use to study the dark matter. So definitely, this is another motivation to go beyond the standard model. Unfortunately, as of now, what we have from different experiments, as you can see in this plot, there is just a lower limit or a constraint. So that means, like, for example, so of course, here I am talking about the particle dark matter and also a very particular kind of particle dark matter that is known as the weakly interacting massive particle, or known as the WIMP. So there are certain motivations for that, but that's a completely different story. I am not going to get into that detail. And this is the result of one particular kind of dark matter experiment, where the dark matter comes and interact with the nucleon. So it's a kind of collision. And after the collision, the WIMPs or the dark matter goes away, and you measure the recoil of the nucleon. And from there, you just try to plot the cross section. So you can see, as of now, we have no discovery, but we have just some experimental limits. And as you can see, that the limit has changed drastically. If you think for this, like Cosent or CDMS, like few years back in 2030, and if you can look at this future generation experiment like Xenon, Bonton, LZ, Lux, you can see there is a drastical reduction. So in fact, even in BSM theories, it is actually getting more and more challenging every day to actually, have a valid particle candidate for the dark matter. So even although dark matter is a clear hint of a BSM physics, but you need to do certain kind of fine tuning to fit a particular dark matter candidate in your theory. And here is a generic cartoon
excuse me,
diagram.
sir.
Please.
Apologies, please accept my apologies for interrupting you. Could we just remove these lines? It's just really distracting the concentration.
I'm very sorry, but this is something that, it has nothing to do with me. I don't know who did it.
Yeah, I completely understand, but I think something is enabled that made the students who can actually have have done this. This editor pad is there, which is enabled, so we can use the eraser probably to erase these things.
Maybe the organizers can help me, because I have no idea about this such things.
Yeah, I'm completely understand. May I try once with the eraser?
It's up to the organizer.
Okay, sir. Okay.
Yes, you can try.
Okay. Thank you, ma'am.
Okay, then you can try.
No, actually, it's not working from my side.
I think it will
Yes,
not work.
it is not
So
working.
maybe what I can do,
Yeah.
the easiest way, I will just stop sharing my screen and I will relog again.
Yes,
Maybe
that will be better.
Yeah, that will be really great. Thank you so much.
Yeah, you're welcome.
Thank you so much, sir. Thank you so much.
Yeah, I think now it's better. Yeah, it's gone.
Yeah,
So
absolutely fine. Now it's
so
absolutely
I just
fine.
give a cartoon diagram of these different
Thank you,
BSM theories. For example, as you can see, it is very clear from here that although we typically said that WIMP is a valid candidate for the dark matter, but as you can clearly see that there is a certain mass region for the WIMPs, only where it can act as a valid dark matter candidate, that is typically from 100 GeV to 10 TeV. That's all. But there are also other candidates. For example, if you go to the very last mass region, there are candidates like heavy neutrinos or asymmetric dark matter and things like that. And also you can see there is a certain region marked by reddish color. It's already ruled out experimentally. But even then, even inside this excluded region, there is certain, region where maybe we have a hint of dark matter, but as of now, it's not confirmed. It may be a result of the statistical fluctuation, or maybe it's really a signal of the dark matter, and we need to investigate more to understand that. And also something is really challenging about the dark matter, that is this yellow region, which you can see in this plot and also in this plot. This is known as the neutrino background. So this actually appears when you have, just like the dark matter, the neutrino-nucleon scattering. And they're actually coming from different sources, like typically from the early universe, that is the beryllium neutrinos, the neutrinos from the boron, and finally atmospheric neutrinos and the DSNP. So that is the neutrinos, the diffuse neutrino background, which are coming from supernovae. So it has all kind of neutrinos. So this is also something, this problem is there. So we really don't know that if our dark matter scattering cross section is really in this regime, as you can see from my pointer. So it is very difficult for us to understand that whether it is really a dark matter signal or it is some consequence of our limited understanding of the coherent neutrino background. So these are the things on which people are actively working now, and hopefully with more sophisticated experimental setup, maybe in next 20 or 30 years, we will have a better answer about those glitches. So I prefer not to discuss more about the dark matter, but this is definitely one hint of or one motivation to look beyond the standard model. Rather, I will now discuss about some things which is really important, but that is not coming from the experimental side, rather it is coming from the theoretical side. That is actually Mr. Higgs. So now we are going to see three different faces of Mr. Higgs, that is the good, the bad, and the ugly. The good thing is definitely true that the Mr. Higgs is the mass generator. Because of the Higgs, as you can see, that the symmetry remains unbroken in the top level, but the symmetry is broken at the ground state, as we have discussed explicitly during the last class. And that's why we see massive particles. Not all of them, because some of them doesn't interact, they are not interacting directly with the Higgs, like photons or the gluons or the neutrinos. So they remain massless in the context of the standard model, but remaining everything else, they got their masses from the Higgs. But there are two bad things, which are like, because of the measured Higgs mass, that is in the ballpark of the 125 GeV plus minus some fluctuations, it turns out that we're living on the edge. I will discuss subsequently this most. And there is also another problem, that it appears that at certain energy scale, I mean, we have no potentials which are actually having a well-defined minimum. And finally, I will discuss the real ugly phase, that is the unacceptable fine-tuning. All these things, they are actually theoretical glitches. Maybe the nature is actually perverted in nature, and this is how it is. In fact, it is true that the neutrinos are carrying tiny mass, where the top mass is 175. So maybe the nature is designed like that. There do exist fine-tuning in the nature, but naturally, being a physicist, it is our intention to know that even if such fine-tunings exist there, why and how. So the first thing is that living in the edge. So it seems like if you actually make a plot of the top mass and the Higgs mass, how you are going to make this plot, that is way beyond your current understandings. I'm not going to get into that detail, but it turns out that if you plot these two quantities, that is the Higgs mass and the top mass, then of course you know that the top mass is measured very precisely as of now. So that is in the ballpark of 173 GeV plus minus some fluctuations. So it turns out that this 125 GeV Higgs mass, it is actually in a region which is the region of metastability. Now, what is the meaning of the metastability? You can think about something like this, as I have tried to, explain through this cartoon diagram. So you have again a Mexican hat kind of potential, but it's asymmetric. So the one which has the deepest position, that is actually the state of the lowest possible energy, and that is actually your true ground state. But if you move here, it is also the state of lower energy, but not the lowest. But definitely if you compare here compared to here, which I have marked with the unstable, this one is relatively deeper. And that is actually something known as the metastable. So what is the meaning of metastable? So it may appear as a ground state, but it's a local ground state. It is not a global ground state. So that means in the regime of the quantum field theory, or even if you think in terms of your simple understanding of the quantum mechanics, the way you have studied the alpha particle decay, thanks to George Gamow, there are always possibilities of quantum tunneling where we can actually go to the deeper minima or the true global minima. Now, that means it may happen just like this Thanos pinch. At one moment we are here, and in the next moment we all evaporate. But we know our universe is almost 14 billion years old. So maybe the tunneling probability is actually way larger than that. But that is actually one glitch. In fact, if you believe that we should be in the stable region, then one would expect the Higgs mass to be likely more. That is in the ballpark of the 130 GeV, plus minus some statistical fluctuation, but which is not. So this is actually one challenge for the theoretical physicists, or who are actually building or trying to understand like how it actually evolves with certain other quantities, that how on earth we are actually living on a metastable vacuum or on a metastable state. We yet need to understand it in detail. The second problem is that, as I mentioned, that if you remember the Higgs potentials, it was like that. You have a quadratic term and you have a quartic term. So of course, you know, our starting assumption was that both these quantities are positive. Now it turns out, surprisingly, if you try to plot this lambda parameter along with the, there is something called the energy scale. This RG is the renormalization to prime. That is something that's way beyond your understanding level as of now. So I'm not going to get into the details. But it turns out that in the high energy physics, a constant is not really a constant, as I will explain in at your level of understanding later. So we often call them a variable constant or a running constant. So their value, their values are constant if you consider a particular energy scale. But if you change that energy scale, the value of the corresponding constant is going to change. So it is not like pi, which is actually constant, is 3.14257 ... throughout. But it is not like that. So it keeps on changing with, it keeps on changing with the energy. And that is dangerous because it turns out that around 10 to the power 9 or 10 GeV, there is a region where actually this self-coupling lambda, it actually goes below the zero. That is dangerous because if you remember the last day's lecture, that actually gives you a potential which is like that. And that is dangerous because now you have no well-defined ground state. So if you have no well-defined ground state, then how on earth you are actually going to do a theoretical formulation of this model, because your ground state is ill-defined. And in fact, this is infinitely, the ground state may have infinite energy. So this is unbounded from below. So it is like a bottomless well. This is another problem. Now, once again, when you are going to learn more about the particle physics, you will learn that there are certain DSM theories where you can introduce new particles, and the moment you introduce more particles in the theory, it may be new scalar, it may be new fermion, they are going to contribute to this particular running scheme, and they may have the opposite effect as you are seeing in the context of the pure standard model. So they may alleviate this situation and make lambda positive throughout the set of the up to the Planck scale. So that is also one of the motivation, that even if say around 10 to the power 9 or 10 GeV, like you believe that okay, there is no new physics till that, but beyond that, around 10 to the power 9 GeV to the Planck scale, you must need new physics to save the state of the standard model, or to have like the well-defined standard model potential. So this is also another glitch of the standard model. Now, why do I mention, of course, as I said, that I cannot explain what is RG running and things like that, but I would like to give you a schematic idea of what do you mean when we define like it's not a real constant, it's a variable constant. Just to give you an idea, just think about these two pictures taken from an aircraft. So it's the picture of the Kolkata. So when you are really, really above, then basically it's going to be very flat. It is very difficult. Of course, the river is very big, you can see that, but it is rather difficult to identify individual shape of house and things like that. But when you are much below, that is about, close to your landing position or just immediately after the takeoff, you can have a better view. So the moral of the story is that if you want to see better, you have to come closer. Or I can transmit this information in the context of the particle physics. If you want to see better, come closer, and that means invest or spend more amount of energy. So now I am going to give you a concrete example where you can see that how it is happening. So suppose you place this blue one, it's a naked negative charge in a position, whatever or wherever. Now, normally the way we used to do, we actually do this Coulomb scattering and things like that, and assuming alpha to be 1 by 137. But there is a problem when you move from quantum mechanics to the quantum field theory. When you move to the quantum field theory, there is something known as the vacuum polarization. So it says that the vacuum is the infinite collection of these tiny dipoles, positive, negative, positive, negative, positive, negative. So the moment you place a negative charge particle, so this vacuum, I mean, this infinite many pairs of dipoles which are available in the vacuum, they get attracted, they're like the positive end. And so overall, there will be a huge amount of charge pile up around this naked charge. So when you are really far above, what you are going to see, you are going to see a kind of large shield of charge, and your naked charge is actually hiding in between that, that surrounding sphere. So definitely you will see a lower charge because the actual charge is somewhat screened by this other tiny dipoles. But suppose you increase your energy and you come a bit closer, say you have invested an energy of the order of 100 GeV. So this 81 GeV is precisely of the order of the W boson mass. But then that means when you are a bit closer, that means you have already like crossed a few layers of these sheets. And now, of course, there is still some shielding, but you will have less amount of shielding when you are that far and now you are here. So you will see or you will measure an enhanced amount of charge. So clearly, alpha, which is given by E square by 4 pi is a global constant, but the value of U will change and I will have a different value of alpha because now your electric charge, which you can see or you can measure, has increased. So of course, in this way, if you want to see the true charge, you have to expect, you have to go to immediately next to that. That means the distance of separation should be 0 and you have to invest in infinite amount of energy. That's just for theoretical physics. So the moral of the story is that in the context of high energy physics, value of some parameters, they actually depend on the associated energy scale. So for example, if I am doing, if I am using alpha for my calculation, say right now at your college, I'm going to use 1 by 137. But if someone asks me to do a calculation in the context of LHC, then I cannot use alpha is equal to 1 by 137. I have to use the value of alpha, which is available at 14 TeV or 7 TeV energy. Otherwise, I'm going to introduce error in my theoretical calculation. So the difference between the theoretical predictions and the experimental observation is going to be large. So it is very important to use the value of the parameter at the correct energy scale. This is just a schematic or a toy example to understand the running of the lambda with the energy scale. So, moving on, now I'm going to end this section with the most horrible thing, that is the unacceptable fine tuning. Now, unfortunately, in order to explain that, I need to use certain terms which are way beyond your current level of understanding. So that is the reason what I have tried. I have tried to give you some something. Once again, thanks to your Jadip sir. So I'm still trying to confine myself in the kingdom of the quantum mechanics. Now it turns out that even in the context of the quantum mechanics, you can use the Feynman diagram to study the perturbation. I mean, unfortunately, it's not possible for me to have the detailed derivation, but you can do. So just to give a schematic example, consider a free harmonic oscillator, one-dimensional, of course, which are perturbed by a cubic term. Now, I can make a diagrammatic representation of this different interaction. So if I want to have diagrammatic interaction, representation of this square term, this is actually like a straight line, which is actually a bilinear terms. Why? So technically, you can represent one x as one line. So if I join two together, so that means at one point, two of them are meeting together. So indeed, although it looks like a line, but it's a bilinear term, and it's proportional to omega square. But apart from this, I also have a term which is cubic in nature. So I can make a graphical representation of this like a Y, where the strength of this particular diagram is proportional to epsilon, because epsilon is the term. Why it is epsilon and why it is not epsilon by 6? For that, you have to study the Feynman diagrams in the context of quantum mechanics, and there is something called the symmetry factor. That's how the 6 gets cancelled. So there are 6 different ways how you can write this diagram. Now, if I actually join two of these diagrams together, so I will eventually get a diagram like this. So this is like an epsilon square interaction, which you can directly derive from the Hamiltonian. And if you try to study the perturbation methods in the quantum mechanics using the Feynman diagram, this is precisely a second order correction. How to do that? You have to study that things. You have to learn certain other things like how to write the propagator and things like that, but I'm not going to get into details. But the interesting story is that if you forget about this block, you see that there are two external legs, just like this bilinear diagram. So although it's an epsilon square contribution, but at the end of the day, it is going to be, or it is going to appear like a correction in your bilinear terms if you put epsilon is equal to 0. This is exactly like the way we used to study the perturbation theory. You put epsilon is equal to 0. Normally, you expand your perturbed energy En as En0 plus epsilon En1 plus epsilon square En2 like this. So this is like a epsilon square En2 correction, but you are adding everything with the En0 with your original energy. So just like that, we are actually going to add this contribution with your bilinear terms. So you can consider this as a higher order correction for your bilinear terms because you have some new interaction in your theory. Now, exactly in the context of the quantum field theory, you can do similar things in the context of the Higgs mass. So as I mentioned during the last class, that a mass is something like you can have one line and one line and you can join them together. So this is the graphical representation of a mass term. But if you go to the standard model, so there is this lambda phi 4 kind of term. So that terms can trigger cubic and quartic interaction for the Higgs. And clearly that is going to give you diagrams like these and these. And on top of that, you know that in the context of the standard model fermions, the Higgs, the Higgs field, it also interacts with different quarks and leptons. And that is how actually it helps them to get their masses. So there will be also some diagrams like this. Just a quick word that I have intentionally picked up only the top and nothing else because you know top is the most massive object. It is even heavier than the Higgs, that is 173 GeV, whereas the remaining quarks of the leptons, they're much, much lighter. That is the reason. And because it is heavy, so if you remember that Tarpit diagram, it heavy means the way or the strain via which it couples to Higgs, it's the largest one. So that is why I have actually chosen this diagram. Now, there are ways in the context of the quantum field theories where you can connect or calculate these diagrams. Now, when you are going to calculate these diagrams, you're going to see that there are certain contributions which are very, very, very large compared to the fact that the Higgs mass that we measure experimentally is only 125 G. So these are known as the quantum corrections. And here I have just shown you just maximum second order correction. Second order means like quadratic in nature, like 2 lambda, 2 YT. But when you are going to do the entire series, just like the perturbation series, epsilon square is not the n term. Then you have epsilon 3, En3, epsilon 4, En4, like that. So those are like the higher order corrections. Here also, you are going to get a series of diagrams. And from there, you are going to get more and more and more contributions. So now the question is that, of course, this is from the theoretical side. Now the question is that when you have so many diagrams with exorbitantly large values as predicted by your theoretical correction, how on earth the experimentally measured quantity is such small? So that means there must be some strange or remarkable or horrible cancellation in the context of the concerned normalization procedure. Why it is such fine or such extremely fine-tuned as of now, we have no clue. So as I said, one belief is that maybe the nature is perverse in nature and that's how it is. But being a theorist, it is natural for us to ask that why such amount of fine-tuning? And this is precisely the reason that if you believe that your standard model is a theory which is valid all the way up to the Planck scale, then you're going to get such horrible corrections. For those who have some idea about these things, you can always argue, okay, maybe standard model is not a theory which is valid up to Planck scale. Fine, let's assume that standard model is a theory which is valid up to 10 to the power say 4 GeV, fine. But in both cases, you are forced to end with the existence of BSM physics. If SM, that is the standard model, is a theory up to the standard model, up to the Planck scale, then you need to explain that how such exorbitant amount of large correction, which is coming from the quantum correction, they are tamed or they are not spoiling your experimental observation, which gives you only 125 G. So you need BSM physics. If you believe, okay, these corrections are finite because standard model is say working only up to 1 TeV or 10 TeV. But then what's beyond 10 TeV? How to study the physics from 10 TeV to Planck scale? So again, you need BSM physics. So this particular phenomena, the quantum corrections, indeed a clear indication, of course, from the theoretical side of the new physics beyond the standard model. And this is exactly like asking the question that in spite of such large quantum correction, how the mass of the Higgs is only 120 GeV and not as large as the Planck scale. I'm sorry, it should be in the superscript. I mean, somehow it got misplaced. Now you can ask that why you are calling it fine tuning. What is the level or why it is? I mean, fine tuning is there in several places in the nature. By why it is fine tuned? Just to give you a story, just consider our famous example or the known example of the solar eclipse. To have the solar eclipse, this distance, as you know, it should be very precise. And how precise? That should be at the 0.05 sigma level. But if you would want to compare this tuning with the precision needed to predict the major Higgs mass, you see, it is 10 to the power minus 33. So you can now understand that that is why we are pissed off with this incredible amount of fine tuning. So collectively, all these things actually indicates or motivates you to study or to prove physics beyond the standard model, but that's not all. There are several other, like flavor puzzle. Why the top quark is so heavy compared to say the up quark? Another thing is that we often mention about the electron and the positron, but electron is something that you can see frequently, but positron is not something you can see very frequently. So why there are more matters compared to the antimatters? This is a problem which is popularly known as the baryon asymmetry of the universe. This is also something about which standard model, as of now, doesn't provide a very nice and peaceful explanation. Also, we initially, and that is why you remember that I start with this example that fundamental means in terms of a few parameters. Now, a few means should be a few. Now, it turns out when you are going to probe or learn about the standard model, there are actually 19 free parameters. From a theorist viewpoint, 19 is an exorbitantly large number, which is very hard to digest because we would expect that if it is really fundamental theory, it should be explained in terms of say 5 or 6 parameters, which is not true in the context of the standard model. So these are of course all theoretical motivation, but this baryon asymmetry or this flavor puzzle, they are observational fact. So collectively all these things, and of course there are many more. For example, why gravity is not included in the standard model, just to give you one option. So all these glitches or all these shortcomings collectively motivates you to go beyond the standard model. Now, the problem is that if you try to go beyond the standard model, there is not a single option. In fact, there are numerous number of options. Definitely one of the very big popular chunk is the supersymmetry, also known as the SUSY. And of course, there are things like extra dimension and exotic model, and then some sequential standard model where you have 4th generation of quarks and things like that. So, but the problem is that somehow all these new theories, they also have their own shortcomings. So you are actually trying to, this is actually something like you have lots of rats in your house, and to remove them, you actually try, or you think that, okay, maybe I should try to have a cat to get rid of them. But it started out, okay, you get rid of the cats, but now all these rats are now gone. But it turns out that actually now that cat is missing with your life. So you start thinking maybe I should try to have a dog to get rid of this cat. So this is like a kind of infinite amount of change. So that is the reason why even inside these individual theories, there are several versions. For example, if you go to the SUSY, I hope you all can see my pointer. The initial theory was MSSM, which is the most popular theory, that is the minimal supersymmetric standard model, that is exactly the supersymmetric copy of the standard model. But it turns out there are certain problems even inside the standard. So people, think about some more elegant alternative, which are like the next to minimal standard model, that is NMSSM, and in this way you have many more theories. Some of them actually now somehow SUSY or supersymmetry as of now is the most popular candidate for the BSM theories. Why? Because it turns out, as you can see from this cartoon diagram, that SUSY as a BSM candidate, it actually roughly answer almost all the standard model problems. For example, it gives you the dark matter candidate in terms of the lightest supersymmetric particle. It explains the origin of this electroweak symmetry breaking, aka EWSB. It gives you unification or origin of matter, origin of flavor, new forces, a lot of things. But other theories, they are good at certain limit, but they cannot provide unique answer to all the shortcomings of the standard model. So any detailed discussion about the BSM physics is definitely beyond the scope of this lecture. That's a completely altogether story. But collectively, the take-home message is that standard model is very good. And if you remember the last class, so I have shown you explicitly that it is so good that the observed experimental discrepancy between the theoretical prediction of the muon G-2 and the experimental measured value of the G-2 is in the order of 10 to the power minus 10. It's extremely precise, but yet there exists rooms for going beyond. And these are some of the elegant alternatives. Unfortunate thing is that these are theoretical alternatives. As of now, we fail to have any experimental evidence of these BSM theories. There were several excesses, as you can see if you are following the literature, there were several excesses in the context of the LHC or other experiment. But as of now, with more data set, people realize that they were mere statistical fluctuation. So apart from neutrinos, as of now, we have no experimental evidence of physics beyond the standard. So that's the end of lecture 2. And now I will concentrate on the experimental detection of the standard model. Of course, as I said, I'm not going to get into the detail of the experiment because you already have studied some of these techniques in your nuclear physics course, like the detector principle. So I'm not going to explain like what is the detector, how it is work, what is photomultiplier tube, how do you detect things in the sensor. Rather, what I'm going to do, I'm going to give you a complete picture of how you are actually going to detect different particles at the experiments and why a particular experiment is designed in a particular way. So let us start today's lecture, that is particle physics at the experiment. So I'm going to start once again with the LHC, which is the biggest collider as of now on the Earth. So there are some interesting facts. So as you know, it's a 7 TeV proton colliding with another 7 TeV proton. As of now, we haven't observed the 7 TeV collision. As of now, we have 13 TeV center of mass energy. But when LHC is going to restart, it's going to go up to 14 TeV. And if you remember the way I have introduced this natural unit system, few class during the first class, this amount of energy will offer you a chance to see a length scale which is of the order of 10 to the power minus 20 meter. So if you don't see anything more fundamental compared to quark or lepton till this length scale, so that means up to this length scale, whatever we observe in the standard model, they remain elementary in nature. Now there are two things you can ask, that what was the motivation to have a proton-proton collider rather than have an electron-positron collider? You will see it later. The problem is that when there is a charged particle in motion, it actually emits some radiation, which is known as the braking radiation or Bremster law. Now it turns out that braking radiation is proportional to 1 by mass square. So now you can clearly see that why protons were our favorite choice. If you actually consider an electron, which is just like half MeV, so it is actually 2000 times lighter than a proton. So if instead of proton-proton collider, if you would have tried to build an electron-electron collider of that energy, so then you can calculate the amount of Bremster length, which is exorbitantly large compared to the case of the proton. So that means you constantly need to feed energy from the outside to maintain, their energies, because they are losing a lot of energy due to this Bremsstrahlung law. That is one of the reasons why electrons colliders are used for the precision studies with lower center of mass energy, whereas the hadron colliders, they are actually used for the discovery, because with proton or with antiproton, you have a lesser amount of energy, and you can actually, make, with this low energy loss due to Bremsstrahlung, you can actually excite them up to a great high energy. But of course, this is the good phase, but there is also a bad phase. The bad phase is that leptons are elementary, whereas proton is not an elementary object. So basically, although we are calling actually a proton-proton collision, but when you are going to learn more about it, it is actually the head-on collision between individual constituents of a proton. So you have quark, you have gluons and everything. So the problem is that apart from the desired event of interest, you are also going to get many unnecessary things. So they are known as the hadronic debris. That is actually a big problem of the LHC. So basically, LHC is definitely a discovery machine, because you can have proton with very high energy compared to the electron collider. But also, apart from the desired event, you are going to have different other, garbage or unnecessary events, which you need to eliminate very cautiously to study the signal of interest. So that is one problem of this one. So many people, that is the reason they believe that we should actually optimize between electron and proton, and that is why, which is known as the muon collider. As of now, this is just a plan, but there is a plan of building one muon collider which is going to operate at 4 TeV, 4 TeV center of mass energy, and we are going to use this also like a discovery machine and also for the precision studies, because muon, just like electron, it's also elementary object. But, and you can also understand that why muon is more favored compared to electron, because muon, although it's elementary, but it is 200 times heavier than an electron, because that is what, if you go back and take a look at the mass spectrum, you can see. So with muon collider, of course, there will be Bremsstrahlung, the breaking radiation, but the amount will be 200 times smaller, and actually 200 square times smaller than individual electron. But the problem is that muons, they also decay. Although the lifetime, because like muon can decay into electron in a few microinverse, as I have discussed earlier. So these are actually, the pros and cons of building a muon collider, but we are really hopeful that at some point of time, we are going to build a muon collider to study more interesting properties. So what is the biggest success of this Large Hadron Collider? Of course, definitely the Higgs discovery. Now you can actually criticize me that why I am actually introduced only about the Higgs discovery, because if you go and take a look at the Atlas and the CMS web page, there exist a lot of discoveries actually. So for example, we have discovered some new pentaquark and pentaquark from the LHC, but Higgs was like something really drastic which has changed the fate of particle physics. That's what I'm bothered about the Higgs discovery. And unfortunately, nothing DSM till date. We are still hopeful. And here you can see a list of all the Large Hadron Collider detector and their abbreviation and their detailed name. I mentioned them intentionally because typically most of the times people are talking about Atlas, CMS, ALICE and LHCb, but there are 5 more detectors. And you can actually ask why so many detectors, because when you are developing a detector, you are always designing a detector for a particular purpose. As you will see subsequently, different particles, they actually interacted, the way they interact with the matter is completely different. So it is extremely difficult to build one detector which is going to detect all possible candidates. You can't. So that is the reason why we have so many detectors, and each of them are precisely or designed in a particular way so that they can achieve certain physics goals. For example, in the context of, like this proton-proton collision, and typically it's a convenient way to assume that this collision is taking place along the z-axis. So if you try to measure something along the z-axis, you need to be very, very careful, because that is the direction where the collision is taking place. So it is expected that there will be so much unnecessary garbage or uninterested event in this direction. So you need to design or place a detector very, properly so that it can detect. It turns out this LHCA, that is the Large Hadron Collider Forward Detector, it is precisely designed for that purpose. It cannot really detect even which is far away from this central axis. For that, you have some other detector. So every detector is designed or built for a particular motivational or for a particular purpose. Now, Atlas and CMS, they are the biggest one because like roughly 3,000 scientists and engineers are working in each Atlas and CMS. And they are the kind of most celebrated ones, especially after the Higgs discovery. And they are like the general purpose detector. And it is mainly Atlas and CMS which are looking for the beyond the standard model physics, aka the BSN physics. Now, before we move on, let us just quickly take that LHC is not the first of its kind. So let's take a look at the collider which were built before LHC and which we plan to build after the LHC. So of course, here I just mentioned a few of them. There are many more. In fact, there are detectors like Petra and Hera, which I haven't mentioned here. So I'm just going to mention some one which are historically very important. Others are also important, but in my understanding, they're more important. The first one is definitely the Large Electron Positron Collider, also known as LEP. So E for electron and P for positron. So it stopped its operation during 2000 and the center of mass energy was 200 GeV. Unfortunately, it was not possible for the LEP to discover something, but it helped us to understand better, the quantities of the standard model. For example, it helped us to measure the properties or the masses of the W and the Z bosons way precisely after their discoveries at the sun. So, in fact, if you are interested, you can go. There is a full nice set of literatures which are available, which is known as the LEP legacy. In fact, this particular experiment was so precise. It was, a part of the LEP was beneath the Lake Geneva. So even if some boat is going on top of the Geneva, the LEP was even sensitive to that boat movement. So you can understand the level of accuracy of the precision, and you must, appreciate that. Then there was the next big detector, which is Tevatron. Unlike LEP, it was a kind of proton-antiproton collider. And finally, it stopped its operation during 2011. So here the center of mass energy was around 2 TeV. And the most important discovery of Tevatron is in terms of the top one. Now, of course, the LHC is running at the corners. It started from 2010. And what's next? And one more interesting thing is that you should realize or you should appreciate, the way the experimentals are working. The circumference of this Large Electron Positron Collider was 27 kilometers, and that is precisely the circumference of the LHC. So even when they were doing this E plus E minus collider, they already, thought of this proton-proton collider. So that is why they made it so big. So this is called the future vision, and that's why they are way ahead of us. Now, one possibility beyond the LHC, because LHC is going to continue till 2025 or so. So one possibility is to think about the high energy LHC. These are all proposals as of now, because we really don't know who is going to sponsor that amount of money. So it's at 27 TeV. There is also another proposal of a 33 TeV collider. As of now, these are all dreams. And then, of course, if during the remaining time, that is from 2021 as of now till 2035, that is the length scale of the LHC operation. If we have some discovery, then of course we'd like to have more discoveries. So one possibility is to have some future circular collider, again with the proton-proton target, and to go all the way up to 100 TeV. So this way we can actually probe 10 to the power minus 21 meter of length scale. That is one order more than the LHC. Also, there is another plan to have collider with electron positron. Of course, we cannot actually push the energies too high because of this radiation loss, but we are going to have between 90 to 350 GeV for electron positron collider, and we are going to use them for precision study. And for example, we can use them as a Higgs factory. Of course, LHC has discovered Higgs, but like as I mentioned, that LHC is also something which is producing a lot of garbage. event. So it is very difficult, to look for the correct event from there. So for that, we actually need electron positron collider. So that is actually a planned one, and we plan to study more about the standard model. And this one is particularly important if we fail to discover anything new apart from Higgs at the LHC till 2025 or till 2030. Then it would be interesting to see, like, look for maybe the new physics is there, but maybe it is way heavier. So direct discovery is not possible at the experiment. But maybe if we actually probe the precision properties of the standard model particles, so maybe the way they are interacting with the BSM physics, although very weakly, it can reveal some deviation from the standard model prediction. But definitely for that, we need electron-positron collider and not the proton-proton collider. Now, I would like to, before I actually jump into the actual physics case, one important thing is that we often consider that it's a high energy collision. I mean, people are always like, I am doing high energy physics, but how high really is high energy? It is nothing if you consider our length scale. So just to give you one practical example, say if you consider a tiny, say, ping pong ball of the order of 1 gram mass and moving with a speed of 5 centimeter mass second. So the 70 eV is actually lying the kinetic energy of this thing. So if I actually throw a 1 gram of ping pong ball with 5 centimeter per second speed at you, of course there will be some impact, but you will practically feel nothing. But because our length scale is way higher compared to, or to absorb this amount of kinetic energy due to impact. But if you compare this at the length scale of the proton, then it is exactly like this head-on collision between two massive cars. So this is devastating. So it is the length scale which actually makes you or justifies the word high energy. And just to give you a kind like a practical compare, you can see that the typical kinetic energy of a 9 millimeter calibrated bullet, so it is actually 490 joule. So it is, as you can see, it is roughly 10 to the power 8 times larger than this one. And of course, you can die with a bullet, but you cannot die with a ping pong ball. So high energy is really high if you go to the subatomic scale. That's why we call it high energy collision. But it is not a high energy if you consider our world, that is the macro one. So this is just to give you some idea. Okay. So now let us try to see how a modern particle detector works. It turns out that any modern particle detector, there are 3 main parts. So the first one is tracking device. What is a tracking device? So basically here we apply some magnetic field. Sometimes magnetic fields, and sometimes you don't even apply magnetic field, but let us assume that you are applying magnetic field. Now and these materials are designed in this way so that whenever a charged particle actually moves through that material, it actually leaves a track. So those tracks are given by solid lines. And here actually you can see a cartoon diagrams where I have represented pictorially every possible thing. So clearly, if it's a neutral particle, then they cannot interact with that medium. So they will leave no mark in the tracker. But if it's a charged particle, and I say that I have already applied a magnetic field, and this law, the equivalence relation between the centripetal force and the Lorentz force is well known. Of course, it's a non-relativistic formula I just wrote down. You need to, at the length scale of the LHC, you have to use it properly with the gamma factor. So you can see that whenever there is a charged particle, they are going to get bent, and depending on their charges, they are going to put mark. I'm not going to discuss everything in detail, but just consider this one. I hope all of you can see my mouse pointer. You see that it's a neutral particle represented by dark red. It went up to that length. Now, if a neutral particle is decaying into a pair of lepton, from the charge conservation principle, we know if one is electron, then the other must be positron. They have different charge, so they will bend in opposite direction. And this is exactly you can see here. And there are also other things. For example, HSCP is something like heavy stable charge particle. One word of caution, heavy stable means stable at the length scale of an LHC detector, not universal, because then we are going to get some, charged dark matter as of now, which we haven't encountered till now. So these are heavy stable charged particles, but at the length scale of the LHC detector, like maybe they are decaying, after traversing say 50 meters, but they don't have an infinite lifetime. And this is a celebrated diagram which you must have encountered in your nuclear physics course. So this is the bubble chamber diagram, and I'm sure that you have studied the mechanism of the bubble chamber, cloud chamber, and all these things in your nuclear physics course. The second part is known as the calorimeter. Now the role of the calorimeter is actually twofold. First, it stops the particle. So that clearly means that it should be some high density material, because if Usain Bolt is running and if you're trying to stop him, you need to have people like Mike Tyson standing in the queue, so that the impact is so large so that you have a chance to stop the guy. So it should be some high density or high Z material. So this Z is the atomic Z. And the second thing is that it must be designed in a way so that it can measure the energy loss, because only then we have a chance to measure the energy of the incoming particle. And definitely, for this two part, we need actually two different kind of materials. So one, high density material to stop the particle, and second, some active material which is going to measure the energy loss and thereby offer us a chance to reconstruct the particle energy. So here I actually just give you a schematic diagram of what is actually happening inside and inside these two parts. So this tracker is something that I just discussed during the last slide. And here you can see when I have an electron and positron, they have a track. When I have proton, pi plus minus, k plus minus, these are all hadrons, as you know, and p and k and pi. So some of them are baryons and some of them are mesons, as you have already studied in nuclear physics course. And finally, I have neon. And you can see, for example, electron and photon. Photon being neutral, as you can see, it leaves no trace in the tracker. But because photon interacted via the electromagnetic interaction, so photon and electron, they are going to deposit their energy in the electromagnetic calorimeter. Whereas the hadron, they are going to detect their energy mainly at the hadronic calorimeter and sometimes also in electromagnetic calorimeter. Why? We are going to see later. The neutral hadrons, they don't deposit any energy in the electromagnetic calorimeter. They directly deposit their energy, like neutron and k0, they directly deposit their energies at the hadronic calorimeter. Finally, neon, it can actually go all the way up to the very last, and we need special mechanism to detect that. Why? Once again, I will discuss later. So I'm not going to discuss about how explicitly these high density materials working, what is the working mechanism of the plastic scintillator and things like that. These are something that you can easily figure out in your textbook material. Now, the final part, that is the particle identification detector. So it actually, so this is actually the final part. So it actually measures the velocity of the particle, and on top of that, it actually borrows the information about the measure momentum, as you have already witnessed in the tracking device. By combining this two information, it actually tries to extract the mass of the particle and hence its identity. So of course, there are 4 different parts, which are like cathode strip chamber, GEM, the gas electron multiplier, the muon drip tube, and resistive RPC, resistive plate capacitor. They have their different roles and different mechanism of detecting a particle. But one important thing is that the presence of this large amount of iron core. So they are actually used to slow down the particle. And in fact, it is the muon which actually escapes all other detector, but finally it reveals its identity and deposits all its energy only in here. So this is roughly known as the muon chamber. And just to give you the detailed idea, putting all the 3 pieces together, I gave you this slice of the CMS detector. So CMS, the diameter is 14 meter, and it is actually the smaller general purpose detector. For Atlas, this is 22 meter. So the radius is 11 meter. But for the CMS, the radius is 7 meters. So you can see, so this part is what the collision is happening. Then you have charge tracker, and as you can see, the red electron, the other charge particle, they actually deposit their they have a kind of continuous line at the tracker, and they have a bending also due to the applied magnetic field. Finally, when you see this green portion, that is actually the electromagnetic calorimeter, where you can see that these particles which were represented by blue dot, it is nothing but a photon which cannot interact with the tracker because it's neutral, but it deposits all its energy in the electromagnetic calorimeter. The red line represents an electron. It has a bending in the tracker because it is charged, electrically charged, so it leaves its mark in the electromagnetic in the tracker, and finally deposits all this energy in the electromagnetic calorimeter. Now, if you think about this solid blue line, which is actually the charge hadron, they moves all the way through this yellow portion, and they leaves all their energy in the hadronic calorimeter, which is known as the HCal, and this electromagnetic calorimeter is often abbreviated as ECal. And in the same way, if you consider the neutral hadron, they also moves all the way and deposit their energy in the hadronic calorimeter. But the muon, it goes, or there is a bending, of course, because it is also a charged particle, but it moves all the way through and finally deposits its energy at the muon chamber. So there is one question important to understand, as you will see later, that why, even being a charged particle, muon can move all the way up to the muon chamber and escapes detection at the electromagnetic calorimeter. We will see it later. And of course, in between you have the superconducting solenoid, and you can see that the magnetic field is also not uniform. So here you have 4 Tesla, and here you have 2 Tesla in the muon detection system. Okay, so I will start with photon. So how we can detect a photon? The way we can detect a photon is that how it actually interacts with the matter. So there are 4 possibilities. One is the coherent scattering, elastic scattering, that is the Rayleigh scattering. But to be very honest, at the LHC NRE, those chances, I mean, of course, as you can see that in this plot, I haven't plotted the Rayleigh scattering, but it is there, but it is not, it is very minimal. Then there are 3 main things. One is the effect of the Compton scattering. You have already studied your Compton scattering, and as you can see, especially when the photon energy is low, the effect of the Compton scattering is really dominant. And you also have the photoelectric effect, which you have also studied in your course, and that is one of the way of understanding I mean, one reason to move from classical mechanics to the quantum mechanics. But also, as you can see, that the photoelectric effect is not really the dominant one. In fact, if you have Compton scattering, it actually lies below the Compton scattering, and it is practically valid for low energy photons. The main important thing is that when you have high energy photon, of course, with a certain threshold, that is, the energy must be greater than the rest mass energy of 2 electron. Then basically, for high energy photons, it is the pair production mechanism which actually dominates, and so basically it's a photon which gets split into E plus E minus, and eventually we detect that. So this is a typical diagram of how a photon actually generates the shower. Why we call it a shower? Because of this thing. So a photon is getting splitted inside the material. So there is one word of caution. Remember, this is actually happening inside the material. So here you cannot blindly apply the law of linear momentum conservation. Normally, it is like photon going to 2 electron positron. But here it is happening inside the material, so you cannot just apply this 2 photon going to 2 object. Because, and why that is important? Of course, if you have a massive particle and it is decaying into rest, no problem. They can go back to back. But a photon being a massless particle, there is no rest frame for a photon. So it is always 2 photon going to electron positron from the linear conservation, from the linear momentum conservation. But inside the material, it is not happening in the free space, it is happening inside the material. So that particular aspect has been already taken care of by a more complicated equation. Anyway, the photon is, getting split into electron positron. But wait a minute, electron is also a charged particle, so they can also emit radiation, brainstorm. This photon can further split it into E plus A minus. So in this way, there will be a shower of electron and photon. And this shower is eventually going to deposit its energy at the electromagnetic calorimeter. You measure the energy and you have information about the incident particle energy. Given that you have a 10 MeV mega electron volt and a 100 MeV photon, so it is expected that the one which is coming with 100 MeV, it will actually produce more showers. And you detect all these things, and by which you can have a proportionality constant, and you can actually probe the incident particle energy. So I just give a schematic, diagram, like how they are actually, depositing their energy in the material. Of course, as you can see, that if you use lead, it is better because then the penetration depth is actually a bit larger. And if you use rather, because for lead, Z is 82, but instead of lead, if you use things like aluminum and lead, because the Z are smaller, so you have a completely different thing. So that clearly gives you an idea that why use of high Z material is beneficial. Actually, if you work out the formula, it is proportional to Z. So higher Z materials means better decay length and better chances of detection. Now, the next question. How do we detect an electron? So, if it is about the electron, there are actually different mechanisms. First of all, there are scattering, something that you are going to learn when you are going to learn quantum field theory. So there are things like molar scattering, Bhava scattering, and things like that. But I'm not going to mention these things. Anyway, you can see that they actually dominate only when the electron energy is really low. But the two main mechanism is ionization, because it's a charged particle and it's moving through the medium. How to study the ionization? I don't know whether you have covered this in your nuclear physics course. There is something called the Bethe-Bloch equation. So that is especially important in the context of the alpha particle, the way it actually moves and ionizes the material. So by using that thing, you can study these things. But anyway, you can see that the ionization is really very high when you have moderate amount of electron energy, and it drops with the higher energy. And that is also well anticipated. Basically, suppose someone is running with a great speed, then the chances of interacting with a lot of people who are actually moving randomly in the park is rather less than a people or than a guy who is actually moving much slowly. So when the electron is really fast and carrying a lot of energy, then the chances of ionization actually goes low. The situation is completely different if you consider the Bremsstrahlung and the breaking radiation. As I mentioned, it goes proportional to Z square, that is, it is very good for high Z material. Proportional to energy, so high energy particle means more and more radiation, and inversely proportional to mass. So as you can see from this plot, that it is the Bremsstrahlung which is the main way how an electron, which is sufficiently high energy, loses its energy. Now you can see that is the reason why I wrote in this in bottom the particle tau. Tau is also an elementary particle. If you remember the first class lecture when we mentioned that electron, muon, and tau all are lepton, but the problem is that tau is really massive and it actually decays very quickly. We will also cover that part. But muon, the problem is that muon, that it is going to decay, but if you calculate a muon in its rest frame, it has a lifetime which is of the order of 10 to the power minus 6 seconds. So it has a finite lifetime. So before decaying, it can traverse a finite distance. But the problem is that because a muon is 200 times heavier than an electron, so the Bremsstrahlung loss is very, very small compared to the electron. So that is the reason why at LHC, it is true that the muon leaves its signatures at the tracker, but because the interaction, the room of interaction is rather low compared to that of an electron, we cannot detect a muon at the electromagnetic calorimeter, and it goes all the way up to the muon tracker. And the final thing, the muon chamber, and finally deposits its energy there. And that is why we put this lot of iron material to absorb its energy. So if you would like to detect an electron, a muon in the muon in the electromagnetic calorimeter, so you can see that for that you need a muon of energy. You can actually calculate at least of the order of 1 TeV energy, exorbitantly high energetic muon. Such high energy muons are very, 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 very rare at the context of the LHC processes. So that is why we don't detect them at the electromagnetic calorimeter. So now we come to the second category of particles. As I mentioned, that it's the world of the elementary particles, and we're going to detect them at the experiment. So photons, electrons, proton, electron, positrons, muon, they are the ones which are like the category of the elementary particles. The others are quarks. But as we have discussed explicitly in the first class, that quarks, because they are colored objects and they are also carrying fractional charges, that because the color charges and the color symmetry is actually unbroken in the nature and the electrical charge is quantized, so we can't detect quarks freely. Then how to detect quarks? So it is true that the quarks get produced at the LHC condition, but they get hadronized. And eventually, the signature of the quarks that you can get will be in terms of the mesons and the barriers. That means pi plus, pi minus, neutron, proton, and things like that. So this is a schematic diagrams, for example, how a neutron, after traversing certain distance, you will get it plated into different parts. And the pi naught, it can actually decay into a 2 photon. How? I'm not going to get into that details. It's a very complicated process. This is an anomaly mediated decay, because that's how a quark can, that is how on one side you have some hadronic object, on the other side you have the photon which interacts actually electromagnetically. And this appears a very tricky, because you see pion is a neutral object and photons, they are also neutral object, but still they're interacting with each other. Although the diagram actually gives like a kind of one vertex, but the actual process is way more complicated. It's a loop mediated process, and this is called anomaly mediated process. Forget about such details here. And subsequently, this photon, as we have already seen, will breaks up into a pair of electron positron, and it goes on. That is why often for hadrons, and now these electrons and positron, as you can see, now they are what? They are electrons. They are actually object which should deposit their energy at the electromagnetic calorimeter. That is the reason when we try to detect hadrons and mesons, often a part of their energies are also deposited in electromagnetic calorimeter, and the rest of the energies, which are like the pure hadronic component, which are not going to interact electromagnetically, they deposit their energy in the hadronic calorimeter. So it's a bit tricky. So that means if you want to detect their energies properly, you have to take care of this entire process. You cannot just measure the energy deposited in the hadronic calorimeter and then you are going to get this thing. And in fact, now you can see that why detecting hadrons are way more challenging than detecting electrons, because they really interact in different ways. For example, a part of it actually gives you charged hadron in the final state. A part of it also gives you nuclear factor, like charge hadron means higher, like sigma plus, things like that. A part of it also gives you nuclear fragments. A part of it also actually go into higher excited state and actually finally emits a photon to come back to this thing. So these are all the mechanisms which you have more or less studied in your nuclear physics course. You know, like there are different things, endothermic, exothermic reaction, photon capture, photon emission, things like that. So those are good. And finally, sometimes like if there is an instability, then the heavy nuclei can break into a pair of nuclei. So all these, diverse processes are possible when you are trying to detect hadrons. So that's why challenging hadrons are way more complicated than detecting a lepton. So it gives you neutral charge as well as invisible outputs. Why invisible? Sometimes you're also going to get neutrinos and they are completely invisible because they are interacting so weakly. So at the length scale of the LHC detector, you can't detect them. So how to detect them? We'll also cover that. So this is just a schematic diagram. So as you can see that the hadronic showers, because of the way they can interact, in a different way, you can see that they have a rather, large area how they are going to deposit their energy. And in fact, if you take a look at the bottom two plots, you can also see that the hadrons, indeed they deposit. So this is actually a schematic slides from what actually happens inside the detector. So here you can see that there indeed exists two different components. One is the component which is going to deposit the energy in the electromagnetic calorimeter, and the other is going to give its energy at the electromagnetic calorimeter, because indeed you have two components. Now, how to detect muons and the tau? So muon, as I have already mentioned, so it is the muon chamber which measures its velocity. This information combined together with the momentum measurement at the tracking device gives you the idea about the mass of the particle. And when you see that it is 105, you know that it is nothing but the mean. And that is the reason one, we put lot of this bended iron yolk in the path of the muon. Now, when it's about the tau, the remaining elementary lepton, it's very, very complicated. Tau has a lifetime which is of the order of, at the rate 10 to the power minus 13 seconds, extremely small. So once a tau is produced, it decays almost instantly. But the unfortunate thing is that the tau decays are way more complicated than the muon decays. They can decay hadronically as well as leptonically. So I have represented everything just a schematic way. So a tau, keeping in mind the lepton number conservation, you can see that the electrons, the neutrinos, they are actually arranged in the way so that the overall and the family-wise lepton number remains constant. So they normally give neutrinos and the charged lepton, and we can detect the charged lepton very easily either at the electromagnetic calorimeter or at the muon chamber. But these are all Feynman diagrams. But there is also a possibility when the tau decay hadronically, and it gives you a set of hadrons in the final state. And this is a schematic representation of different possible way how a tau can decay. So as you can see, tau is a charged particle, so of course it is going to leave its mark at the tracker. Then if there is a photon or electron, it gets detected at the electromagnetic calorimeter. But finally, you can also get a series of hadrons. They actually leave their traces at the hadronic calorimeter, and that's how you can measure the fact that it is actually a tau. But you should remain careful about that fact that every time you're also going to get some neutrinos with them, which will escape detection. So the mass reconstruction for the tau is less faithful than that of a muon or an electron. And that is also more important in those of you who are going to probe this thing further. In the context of tau, when it is hadronic decay, there are two terms which is very popular among the experimentalists. One is called the one-prong decay, and the other is called three-prong decay. So I'm not going to get into detail. One prong means one charge hadronic object. That is actually this diagram and this diagram, where you have only one charge pion. And the other is three-prong decay. That gives you three charge particles in the final state. So 3 pi plus pi minus or 3 pi plus pi minus, as you can see. So these are the famous one-prong and three-prong decay, hadronic decay of the tau leptons. So that actually covers the part of the lepton detection. Now, you see, in the context of the LHC, we often heard this was jet detection. Now the question is, what is a jet? Once again, they are typically connected with the quartz sector. Typically, quartz are colored, so we cannot detect them freely. So basically, they combine and they actually appear in the form of color neutral hadron. So a collimated spray of hadron is known as the jet. That is the easiest and the layman's definition of the jet. So, and that is the reason why, and jets are extremely important for the LHC because they gives the experimental signatures of quartz and gluons produced in high energy condition. And for example, like it's a proton-proton collision, and you have then quarks and gluon, which are like the output of this collision, and eventually they form a hadron, and this is they as if they moves like a conical shape. I mean, I will define why this cone is important. And finally, they deposit their energy at the hadronic calorimeter. We measure them, and using all this energy measurement, we try to reconstruct the jet. So jet is something very important. Now, how to identify a jet? For example, this cone I have used to identify it as one jet. How to identify is a jet? It's very challenging, and it is a problem not only for the particle physicists, also for the people who are trying to, combine this in a computer program. This is something called the jet clustering algorithm or jet forming algorithm. This is advanced topic of research, but there are several scientists who have dedicated their lives and still they're working on that, because we are trying to actually achieve the goal of better and better accuracy, so that the jets are very precisely and accurately defined. So moving further, now there is two things which are extremely important about the jet. So as I mentioned, it was not my motivation or intention to give you the detail, but to make you familiar with all the terms that you often heard in the particle physics talks. Now there are two things which are very interesting about this jet formation. So suppose consider decay of a top quark. In the context of the top quark, the dominant decay of the standard or in the standard model is top decaying into a bottom quark and a W boson. And the W boson subsequently can decay into a pair of quarks. That's it. Now, when this top, the mother top, it has low energy, that is less than 200 GeV, you will see a bottom and a W. That is this W, after moving a few distance, it will split it into two quarks. So this B will have a jet. This 2Q from the W will have their jet, and represented by three conical shapes. Now, LHC is a high energy machine. It could happen that this mother top is produced with a reasonable amount of energy between 200 to 300 G. Then this bottom actually goes as it is, but this W is moving in a way so that when it gets split into two further quarks, whatever jets they form, they remain in one. So low energy, three jets. Medium energy,
জয়িতা ওনার থেমে গেল।
হ্যাঁ, আমিও কিছু শুনতে পাচ্ছি না, বুঝতে পারছি না তো।
ওনার ছবিটা দেখো স্ট্যান্ড স্টিল হয়ে গেছে।
হ্যাঁ, সেটাই আমিও দেখছি, লেখা দেখাচ্ছে, কিছু প্রবলেম বোধহয় হয়েছে।
হ্যাঁ, কি হলো বললো তো হঠাৎ করে?
উনি
প্রদীপ্তকে দেখা যাচ্ছে।
এবার দেখা
হ্যাঁ
যাচ্ছে।
হ্যাঁ হ্যাঁ
মিউট হয়ে গেছে, আনমিউট করতে হবে ওনাকে।
করে নেবে। প্রদীপ্ত, প্লিজ আনমিউট ইয়োরসেলফ। শুনতেও পাচ্ছে না।
একটু জোরে বলবো?
হ্যাঁ,
প্রদীপ্ত, প্লিজ আনমিউট। স্যার, প্লিজ আনমিউট।
can you hear me now?
Yes.
Hello,
now I can hear you.
হ্যাঁ।
can you hear me?
Yes.
Hello,
Yes, I can hear you.
can you hear me? Am I
ও
audible?
শুনতে পাচ্ছে না, ও শুনতে পাচ্ছে না। তুমি একটা মেসেজ করো তো, ফোন
Hello.
করো।
We can hear you. আচ্ছা।
Am I audible?
হ্যাঁ, আমরা শুনতে
Yes,
পাচ্ছি।
you are audible.
Hello. Am I audible?
Yes, we can hear you. You are audible. You are audible.
Am I audible? Hello? Hello? Okay.
Now you can hear.
Yeah. Sometimes it is also possible that you have a pair of electrons which are not well separated because they are coming from a mother which is moving very fast. So in that context, there is a possibility at the LHC also to see a pair of electrons clubbed together inside a cone, and that is often known as the lepton jet. So lepton jet is not also something very unpopular, but typically jet means. Now, why this jet is so important? Because how we are going to define this cone size, so inside this object. So as you can see, just because we have defined our cone size differently in these three cases, in one case we have three different jets, in another case we have two jets, and finally we have three jets. So it means that the definition or the number of jets really sensitive to how you are defining your cone size. How to define the cone size, I will also cover that part. So this cone size definition is very important. And this is also important in this way because sometimes the objects, a pair of objects which we are detecting, they are not well angularly separated. So they are like this. Then what will happen given the current resolution? So as I showed earlier, that they are going to deposit their energy into some crystal, and we are going to measure that thing. So these crystals are the building blocks of the electromagnetic calorimeter or the hadronic calorimeter. Now, if they are like very close to each other, then what will happen? Just like this cartoon diagram, both of them will deposit their energy into the single cell, and then it is impossible for us to define them as two distinct objects. So we will call them as one object. That is clearly a misidentification. On the contrary, if they are wide separation, instead of going into a single cell, they will actually deposit their energy into two different adjacent cells. And then we can reconstruct them at two distinct objects. This is very important because sometimes, for example, later when we are going to learn about the particle physics, we will know like few years back, there was this, we observed some 750 GeV resonance at the LHC, and then there was the big debate, 750 GeV, some scalar decaying into a pair of photons, but there was a big debate whether it is actually 2 photon or 4 photon. So there were several papers where you consider as a 2 photon, and there were several papers where you consider as a 4 photon. I myself wrote 2 papers assuming 2 photon and 4 photon. So this is the case. So this resolution is very important. So of course, the way they're planning, they're going to change the detector slowly, and they are going to actually increase the cell size so that it actually gives you better accuracy in detection. Because suppose here also, if you have a smaller cell size, the building blocks of the calorimeter, then you can even detect two objects which are rather closely spaced. But there is also, of course, there is a limit beyond which you cannot go. And that is why that is something that you have already studied in your nuclear physics course, known as the limiting case of the detector. So our detector cannot pick up everything. There is a limit. So there is a threshold only above which it can detect. Now, I'm going to define a few important parameters that is very important at the context of the LHC. So as you know, as I said, the ZZ, the proton-proton collision, we normally consider this as a Z axis. Now, along this axis, measuring something is very messy because the actual collision is going there. So all the remaining things, most of these unwanted, objects, they actually lies close to his Z axis. But one which are really interesting, they typically, if this is the collision, they goes like this. So if this is Z, then they actually moves in the XY plane. So we actually define two quantities. One is known as the pseudo rapidity, which actually is a different way of measuring the distance from the Z axis. And more importantly, it's a Lorentz invariant quantity. So it actually varies from -infinity to +infinity. And this is actually one important parameter to design your detector. For example, low eta means you are actually very close to the Z axis. High eta means you are far away. And also we need to define two more quantities, that is the transverse momentum. because as measurement, any measurement along the z-axis is rather tricky or challenging or erroneous, we actually need to measure things at the transverse momentum. These two also offers two very important distinguishing parameter to identify your signal. For example, suppose your final outputs are moving with very low velocity, then you need to design your detection system accordingly so that you detect those very low PT or the soft object. And these are also two important quantity because you actually need to define some minimum beyond which you cannot go, because there is a limit, and that is the limit of the detector beyond which you cannot go. So, and these limiting values are useful to define the cards. Now, why defining the cards are important? And before that, I will also mention one more thing. So, in the same way, you define two more important characters in the context of the LHC. One is the invariant mass, and this is just a kind of cartoon diagrams where a mother particle is decaying into a pair of particles. So this relation is something that you have studied and is well known. And in the same way, you can also define something called the transverse mass. Of course, these definitions are valid if we assume that both the particle A and B, the daughter particles, they are detectable and they are not invisible, like unlike neutrinos or some stable dark matter particle which escapes detection. There you have to redefine your parameter, and you go to more complicated variable like M2 and things like that. I'm not going to go into detail. And this parameter, which is the square root of delta eta and delta phi, is also important. So this is actually something which determines your cone size. Say if you have two objects which are lying very close to each other, then if I need to define a particular del R to know that whether they're actually two objects or I'm going to treat them as one object. So these parameters, PT, eta, invariant mass, delta, they are extremely important to define some quantity which help us to discriminate or to determine our signal from a huge number of unwanted or unnecessary events. Now, how to do that? The thing is that suppose you need to detect a few rats. Of course, you are going to go into the market and you're going to buy a rat trap. But suppose you need to detect a tiger. You are not going to work with a rat trap. You need something bigger. So the important thing is that you have to arrange your trap accordingly depending on the size of your prey. That is exactly the experimentalists are doing in the context of the LHC. So here I just give you a sample decay cascade. So this is a heavy mother decaying into the first generation of daughter, and they are subsequently decaying here. So clearly, if we go to the more and more and more decay chains, so the particle's energy is going to reduce. So this is actually the secondary daughter. So this is coming from a mother which is smaller than this mother. So it is expected that here the decay products are going to act here with lower PT. That's a lower transverse momentum. So these are often classified as a soft PT object. So these, if I am planning to detect this object, so I need to lower my threshold. In other words, these are like the small rats for which I need to have a rat trap. Whereas this first generation of daughters, they're coming from a fat mother. Now, fat mother means more mass, more energy. So this is going to appear with a lot of transverse momentum. So this is like that tiger for which I cannot use a rat trap, but I need to use a bigger trap. So here I need to put a higher PT cut. For example, just to give you an illustrative example, so maybe applying a PT cut of 20 GeV, like detect all the object which is coming with the 20 GeV, or lower, I can detect this things. Of course, I need to also have an absolute minimum lower, because otherwise I'm going to get unnecessary garbage coming at 1 GeV or 2 GeV or even smaller than that. But here, if I apply a strong PT cut, like detect only objects which are coming with a PT less than 100 GeV, then I can get rid of all those unnecessary events. So detecting soft object or objects which are collinear or moving along to the beam axis is a real challenging task at any collider experiment. So moving further, the thing is that how, and so I just give you one object, like why we need different cards. And now let us restudy this thing in the context of a real life example. So whenever you are plotting some quantities at the LHC, some parameter, there are a number of events which you can detect at the LHC. But the interesting thing is that that same event can appear also from other sources. So here, although these diagrams are rather complicated for your understanding, but these are the sample diagram by which you can get 4 lepton final state at the LHC. A few possibilities, not all. Now, I am interested to study this when they are coming from the Higgs. So I put this red just to denote these things, that whether it is online, that means it's a real particle which produces and then decays, or it's a virtual particle which decays continuously. So if it is a star, that means it's a virtual particle. That means it is not a real particle. So this line goes and then decays. But if it's a real particle, then the decay mechanism is completely different, and you have a easy way of calculating. But those are something that I'm not going into the details. The nutshell story is that this is the process which I'm keen to see, and these are the process which is giving me same final state, but these are unwanted. Unwanted things are known as the background. The desired thing is known as the signal. So now suppose I am plotting the PT of this event. So you see that this red is my desired event and this blue is my undesired event. So now you can see that how this PT cut means a threshold. Setting is important to probe your signal. You see, if I put a PT cut of 20 GeV, then all the events which is coming from the backgrounds are unnecessary things. Their count is actually below my signal. So I can detect my signal uniquely. But if I set a PT cut of 10 GeV, here you see that my undesired background overshoots my signal, and I cannot detect things uniquely, at least in this portion. So depending on this distribution, it is very important to study this distribution at the LHC, because that offers us a chance to detect our signal uniquely. So I just mentioned only a few parameters like PT cut, eta cut, invariant mass curve, as we will see in the subsequent slide. Invariant mass is also another important. For example, here once again I probe all the things, all these 4 diagrams which I mentioned here. So if you plot the invariant mass distribution, you can see only when they're coming from a Higgs, you would expect a peak around 125 GeV as it is given by this red signal. And you see these all are the signals which are coming from this source. So now you can see that apart from the vicinity of this 125 GeV, everywhere else, it is my backgrounds who are the winners. But if I put a cut that no, detect only those objects which has invariant masses, or which have invariant masses in the vicinity of 125 GeV, then I can detect my signal. And you can see only in this portion, it is a winner over the background. Everywhere else, it's a loser. So these distributions and identifying these key parameters are extremely important to isolate your signals from the background. But it is not very easy always. For example, if you have this, another thing is another schematic diagram just to show you that this invariant mass distribution is not very easy. This is just another invariant mass distribution for this 4L system. So you can see that the 4 system, there is a peak at the Higgs mass, fine. There is also another peak, which is actually, if you calculate, this is around the 200 GeV, or to be precise, in the ballpark of 180 GeV. This is also expected because this means a pair of leptons are actually coming from a real Z, and the Z mass, the Z boson mass, is around 91 GeV. So if I consider 2 of them and collect all these 4 leptons, this will actually give you invariant peak around 180 GeV. That means 2 real Z boson. But You can also see another peak, which is at 90 GeV. It seems very puzzling, but indeed there are processes when a real life Z is decaying into a pair of lepton, and one of the lepton actually emits a virtual photon or a virtual Z, and it decays actually into another pair of lepton. So although initially a Z was decaying into a pair of leptons, but finally because of this virtual radiation, because they are very high energetic, it can give you or yield another pair of leptons. So eventually you ended up by getting 4 leptons, but the peak is actually at MZ, that is as 90 GeV. So the job of an experimentalist is not at all easy. It's very, very challenging. So a good experimentalist should also have information and knowledge about the underlying theory and vice versa. Now, the important questions: how to detect the stable neutral particle like neutrinos or the dark matter? Of course, they are stable. So as I have represented in the cartoon diagrams, that they appear completely invisible from the viewpoint of a detector. But wait a minute, there is one tool. We know that the conservation law of the linear momentum. So that gives us a very, very important relation. Negative of all the visible PT is nothing but the PT of the invisible particles. We can calculate this invisible PT, or we can have information about the invisible PT by measuring all the visible PT. That may appear from the neutrino as well as from the dark matter, which is a stable particle which remain undetected or escape detection at the LHC. We measure invisible through a measurement of the visible, and this is how we can detect the neutrinos and the dark matter particle, as you can see in the plot. So this is, of course, instead of missing transverse momentum, I have put the missing transverse energy, more or less equivalent, and this is the number of the event. As you can see that the neutrinos, as you know, they carry really tiny masses. So the peak which is coming from the neutrinos, this is actually near the lower atomic range. Whereas if indeed I have some massive particle like the dark matter, I would expect them to reveal their signal or their signature at the high ETMs. As of now, unfortunately, as you can see, so these 3 dotted lines are 3 theory candidates. For example, this ADD, which is one of the extra dimensional model. So if you want to know more, you can discuss with your teacher, Professor Mitra. I mean, he has one. This is the Arkani Hamed Dimapoulos Daveli model, one of the popular extra dimensional model with 2 extra dimensions. This is a 5-dimensional model, and this is the model where you have graviton. But unfortunately, you can see that these dotted lines are the theory prediction. The expected amount of missing transverse energy I would expect from the theory. But you see now the sad reality. That is the 2012 data. The data remains actually below the theory prediction. If instead of that you would expect a data in this region, then you would have claimed a much anticipated discovery of the BSM scenarios. But unfortunately, the data lies here, which is to statistical fluctuation more or less consistent with the standard model prediction. So as of now, no BSM. But if we observe tomorrow or with more data sets, some event here, that means it's going to be a detection. Now, why do you need to define all these quantities? What is really the work of an experimentalist? The experimentalist is trying to give you a discovery. Now, for that, you need to define something which is defined as the signal significance, which is the ratio of the number of signal events by square root of number of signal events plus number of background events, that is the undesired event. Typically, the number of backgrounds, as you have seen during the last 2 plots, are way larger than your signal event. So you can actually roughly approximate this formula as this. The sad reality is that the number of backgrounds are actually way larger than the number of signals. So this is indeed like, looking for a needle into a pile of haystack. For that, actually defining the correct variable is very important. So I just give 2 cartoon diagram here. to let you know what exactly the experimentalists are doing. So suppose you have some variable A. So this A maybe it maybe missing energy, maybe transverse momentum, visible transverse momentum, maybe eta parameter, that is the pseudo rapidity, maybe the invariant mass. And you see that here, even if you consider any cut, like cut means keep those events or discard those events, it is impossible to know because the background actually wins over the signal. But suppose you design or you improvise certain intelligent other variable where you can see that certain intelligent definition of parameter and the cut can get rid of all the backgrounds and you can get your desired signal. This in a cartoon seems very easy. In reality, this is extremely difficult, and that is what our experimental colleagues are doing day in and day out. So they are doing a really, really critical job to define an intelligent object so that it can yield a 5 sigma discovery. For example, how to define that thing is not very easy. You have to consider case by case. Just to give you one illustrative example, I actually discussed something which is very intelligent known as the displaced vertex. Sometimes it happens that in a collision you have an object which is neutral, but before decaying it actually traverses a finite distance and then it decays. So here it is represented by this. So the primary interaction vertex is where this object is actually produced at the PP collision. And immediately you can get some electron, photon, or gamma or jets from the primary vertex. But there is also some particle which traverse a finite distance and then decay into the known object, that is electron, muon, photons, and jets. But before decay, it traverses actually a finite distance, and this distance is known as the displaced vertex. If it is neutral, then you see nothing. All of us see that a cluster of visible particle, it appears at certain distance, and there is nothing which is tracking it back to the primary interaction vertex. If it is neutral, if it is charged, then of course it will leave its marks in the charge tracker, and then it decays into some known particles. This is what I have also tried to show you, if you remember, in this cartoon diagram when I mentioned like the tracking device. This displaced vertex is a typical or very unique signature of the BSM physics. Of course, even in the context of the standard model, you can have this displaced decays, but very, very small, of the order of millimeter. But in the context of the typical BSM theories, they can go even up to order of centimeter is very typical, but it can even go all the way up to a meter. That means displaced vertex is one of the discriminator which you can use to isolate your BSM background, BSM signal from the standard model background. So that is what the experimentalists are doing. I would like to end this also with something very important, that why we are actually jumping about the 5 sigma discovery. So this is the famous bell curve where I have tried to show you 1 sigma, which means 68.2%, then 2 sigma, that is of the order of 9, and then 3 sigma, that is of the order of 95%. But why it is important? A 5 sigma, does it mean that a 5 sigma means a discovery? No, definitely not. But a 5 sigma prediction means that 99.99994% it is actually coming from the desired event, and it is not a statistical fluctuation. So having something wrong at 5 sigma level means that it is like having 1 in 3.5 million chance that it is a result of a statistical fluctuation and not a signal. So what is the life of an experimentalist when you have a 5 sigma discovery? 1, with more data, try to have a better estimation. Reduce the systematic theory uncertainty is something that is the job of the theorist to do the calculation. For example, better understanding of the QCD, reduce theoretical uncertainty. Experimentalists will try to reduce the systematic uncertainty and try to go for higher sigma. For example, if you go to 7 sigma, that means it is okay, it is 99 point this, it is not. So 7 sigma, if you go, so it is actually 99.9999997. Sorry for the typo. So a mistake at the 7 sigma level means witnessing an event in a fine morning which has appeared only 4 times till now in the history of the visible universe. So you can see that that is what the experimentalists are doing. Next, when you have a discovery, try to measure the basic properties. That is the mass, the charge, the spin, so that you know more and more about this particle. These objects are definitely the job of one experimentalist. Then the important question, to know the origin. That is definitely not the job of an experimentalist, that is the job of a theoretical physicist. Finally, the most tricky part, if we see something DSM, is there only one BSM particle, or there are series of BSM particles? Maybe the one which we have just discovered is actually lying in the lower part of the mass spectrum. So is it alone, or is it accompanied by a series of friends? That is a collective job of the theoretical physicist and the experimental physicist. This is what basically people are doing in the context of the any collider experiment. So moving further, end of LHC. Now let us try to jump into something which we have already seen. That is the neutrino sector. So this matrix, the PMNS matrix, I have already introduced this in the previous lecture. But this PMNS matrix is actually a collection of 3 different matrices, assuming that neutrinos are Dirac particle. That means a neutrino is not its antiparticle, although it is electrically neutral. That means you respect the lepton number, because the lepton number carried by a neutrino is +1 and the lepton number carried by antineutrino is -1. If you respect lepton number, then these are the 3 possible parts which appears in the PMNS matrix. So the first part, so this C and S are the symbol or the symbolic representation of cos and sine. So C23 means cos theta 23. I'm sorry, I forgot to write explain this abbreviation. So the first part is going to give you information about the atmospheric neutrino mixing, that is theta 23. The middle part, theta 13, is going to give you information about the reactor mixing angle. And this is something which has changed post 2012, because it is the time of the Higgs discovery. Also in the same time limit in 2012, we came to know about the real non-zero measurement about this mixing angle, thanks to a series of experiments, Reno, W, and this has been confirmed by several. And this actually changed also the fate of the flavor violation experiment. I also wrote a paper on these things back in 2012. And finally, in the last part, it is going to reveal the information about the solar mixing angle. So these 3 mixing angle, and there is one delta, which is a CP violating phase, the charge parity violating phase, which is typical for a Dirac neutrino. What is the origin? We are not going to explain. So the oscillation experiment actually gives you information about 6 parameters. 3 mixing angle, theta 23, theta 13, theta 12. Sorry, I'm going a bit fast because I also need to cover a few more slides before the end of the talk. The CP violating phase delta and 2 mass square difference. Now the question is that all? No, you need to know few more things, especially when the neutrino is not a Dirac particle, but it's a Majorana particle. So that means, forget about the lepton number conservation. I'm going to treat one neutrino as its own antiparticle. Then the said UPMNS matrix is going to get enhanced. How? You need to include 2 Majorana CP phases, delta 1 and delta 2. It's a diagonal matrix, so it's a 0, 0, 1, 0, 0, 0, then 0, and this is exactly the structure. So the diagonal of this thing. That is there if you consider neutrino to be a Majorana particle. Now, why it is so important to have a Majorana thing? To have the Majorana nature is going to give you some new signature in the neutrino sector, which is impossible with a Dirac neutrino particle. For example, on the left side, you can see the conventional beta decay. This is well known. This is you have studied in your nuclear physics. But if the neutrinos are a Majorana particle, then one neutrino can club together with it, and I can have a vertex where the lepton number is violated by 2 units. This is the celebrated example of the 0 nu BB, or known as the neutronless double beta decay. Oscillation experiment gives you no information about this delta 1 and delta 2, the Majorana phases, but it is the oscillation, it is the neutronless double beta decay experiment. It gives you an information. And without understanding all this detail, you can roughly see, so this is a dedicated Feynman diagram, but look at the left hand side. You have a D and D. So what is the net lepton number? The outgoing leg, 0. What is the final lepton number? You are getting 2 electrons. So delta L is equal to 2. So on left side, your lepton number is 0. On the right hand side, your lepton number is 2. So in this process, you have violated the lepton number by 2 units. That is the territory of the Majorana neutrinos. As of now, we are looking for it. There was a reported by one of the Russian collaboration that they have observed it, but later with other experiments, following experiment or follow experiment, that claim is probably not true, and it probably is probably from some kind of statistical fluctuation. So as of now, we are still looking for it. So this is the current global status of the neutrino experiment. Thanks to my old colleagues, Michel Maltoni from IFT. So I have shared this from his recent paper. So as you can see, that this is precisely what we are actually measuring. So we are measuring the mixing angle 1, 2, 2, 3. So the sine square value and the individual value. We are measuring the Dirac CP phases and the mass square differences. Now, if you remember yesterday's lecture, the last Saturday's lecture, so only when it is about the mass things, we measure the mass square difference, but not the correct ordering. So depending on the ordering, if you go back and take a look at the last day's note, you have normal ordering or the inverted ordering. So in one case, we are measuring 3-1 difference, and the other case, we are actually measuring 3-2. Since we really do not know the exact ordering, so this particular quantity may be greater than 0 or maybe less than 0. So one more important thing, so this one, which I have shown here, this is including the SK data. So SK is the super Kamiokande, which is a neutron detection experiment in Japan. As of now, if we follow this data, so the normality hierarchy is somehow slightly more favored compared to the inverted hierarchy as of the 2020 super Kamiokande data. But it's not confirmed. Maybe with the more data set, this asymmetry will get washed out. But as of now, that is the status. As I mentioned, that for the remaining parameters, the Majorana axis angle oscillation experiments are not going to solve the purpose. So for that, you have to get information from 3 different sectors. One is the beta decay experiment. So for that, the Carl Shui tritanium neutrino decay experiment is something very popular. As you can see that from here, you can have information about the remaining parameters of the neutrino sector, and the current limit is less than 8 MeV. For the neutrinoless double beta decay, which is the most amazing experiment. So this scattering experiment is useful because it can give you some idea about the individual neutrino mass. For the neutrinoless oscillation, for the neutrinoless double beta decay, it can give you some information about the phases. As of now, we just have limit. So this Greda and the EXO, one is at the germanium based detector at the Italy, and this is the xenon based detector at the USA. So these are the current experiment. This molybdenum based target experiment, QP at France, it has started. As you can see, so these numbers are very well precise, and the molybdenum based, this data set, as you can see, it's really most, because this experiment is yet as the development phase. So this is just like their first observation, but this is a next generation experiment, and we hope to have more precise numbers from this molybdenum based experiment, but maybe around 2025 or even later. And finally, we have some constraint on the sum of the neutrino mass from the cosmology. So this is a collection of a lot of experimental probes, WMAP, anisotropy experiment, baryon acoustic oscillation, and things like that. Don't get into the details. But the moral of the story is that the sum of the neutrino mass is really tiny. It's only 0.12 electron volt. So it is actually from the European Space Agency. So, and here you can, if you are interested, you can go through all these things. But this is more or less the collective state of art about the neutrino experiment as we know now. And to end the story, one thing is important, that how do we detect the neutrinos? I'm spending a little bit more time on the neutrinos because it is important, because this is the clear indication of the BSM physics. We can detect neutrinos by two mechanisms. One is the charge carrying interaction when we see a charged electron. And of course, such interactions, when you are going to learn about the standard model, these are the interactions which is mediated by the W plus minus, that the charge electric bosons. That's why we call this neutral interaction. Why they are important? Because they actually give you a charged electron in the final state, which we can detect using the conventional detection mechanism. For example, if it's an electron neutrino, I would expect the electron. And as we have seen in the context of the LHC, this will detect shower. And we can detect that shower and we can detect this thing. So if you see an electron, okay, it is coming from, then, the parent neutrino must be electron type flavor. Similarly, neon, it's rather heavy. So now you need a threshold energy. So neon, as you know, it will penetrate. We can detect that and we can actually confirm that it is coming from a neon neutrino. Tau, it is more heavier. So now the threshold energy is more higher, much higher. And of course, here the detection is really challenging because tau, unlike an elementary electron neon, it is going to decay and you are going to add a lot of different hadrons and leptons and neutrinos. So for a tau, detection is rather challenging. You also have this neutral current interaction. So where the neutrinos comes, they interact with the nucleon and the nucleons recoil. You measure the nuclear recoil and they actually goes away. So for example, one is the coherent scattering. So like neutrino, electron, or this 2H is nothing but the heavy water, D2O, deuteron. So it interacts. So this 2H is actually from the heavy water deuteron. So it interacts with 2H, it gives you proton and neutron and another neutron. So here, neutron is the incoming one, neutron is the outgoing one, but you detect all those, this recoiling hadron, and thereby you can probe the amount of energy transfer. And in the next slide, I'm not going to read these things because this is something that you can see later. So these are the 5 possible broad classes how neutrino detection experiments are classified. You have radiochemical experiments where you detect neutrinos through a charge current interaction. And I also gave some of the experiments which are growing around. Homestake is very important because this is how this Renz and Cons, they actually discovered the neutrinos in the very first time, long back. Then you have liquid scintillator experiment and like the Borexino. So it's actually detects neutrinos via both the way. Inverse beta decay, which is a charge current interaction, and through the nuclear interaction, that is through the coherent scattering. And some experiment like the Borexino, Camland, Minibune, so they are running across the world. And this Minibune is very important. So those who plan to study the neutrinos or the high energy in the later state of their career, so there are some anomaly which is about the 4th flavor of neutrino, which is known as the Minibune anomaly, but beyond the scope of this talk. Then you have the tracking experiment, Minos, the Minerva, and so they also used different kind of these things like the scintillator detector or the liquid argon-based detector. And finally, this water Cherenkov experiment, which are very important. So typically, when you have a charged particle which is moving through a medium, because in the free space, nothing can compete with the speed of light. But in the medium, the speed of the light, this is something that you must have studied, it gets reduced depending on the refractive index of that medium. So in a medium, the speed of the light is not the supreme one. If it happens that because of the interaction of some high energy particle, the electron or the muon, which is produced through this charge current interaction, they're actually traveling through that medium greater than the speed of light in that medium, it actually emits a characteristic radiation known as the Cherenkov radiation. And there are well-defined Cherenkov zones. You detect that and you have information about the parent particle. So they typically use the heavy water. And this is actually one of the most popular type of the experiments where you have the Super Kamiokande, you have the SNO, the Sudbury Neutrino Observatory, and then you have Ice Cube and Antares. They are really the neutrino telescope. So they are actually using because in the Antarctica, this Ice Cube is in Antarctica and this Antares is actually under the sea. So where the water density, where the quality of the water is very pure. And you can actually, so they are although they use the Cherenkov technique, but they are known as the neutrino telescope. And finally, you have the emulsion experiment, and this is very experiment because this is how the donut collaboration, they use this technique, and using this they have actually discovered the tau type neutrino for the very first time. For this you can see the list of all these particle discovery which I mentioned during the second lecture. So to finish up the story, I must mention what we are doing as it in India. This is a pure Make in India project. So this is our INO, the India-based Neutrino Observatory. But as you know, in India, things are rather complicated. Finally, we have a location where we are planning to set up these things. As of now, most the the elementary things are done. So this is actually the resistive plate capacitor which are designed in India. And they have a stack of array how they are going to measure it. And here in INO, we are for the first time. So this is something which is called, it is very unfortunate that because of several bureaucratic complications, we are still not with some result. We haven't published any concrete result from this experiment. But this INO, you must consider it as one of a kind, because this is the first place where we're actually going to use an ion calorimeter. So this is a huge stack of iron, and in between each stack there are this RPC plates. We are going to place it and we are going to measure this thing. Once again, we are going to use the techniques of the charge current interaction. So INO will give, INO will do two things. First, and also there is a magnetic field. So first, it can reveal the identity of the neutrino, and it can also measure the energy of depositing. So the main target of INO is to study the atmospheric neutrino oscillation, and thereby it is more biased towards the neon neutrino detection. But with time, maybe, if they have some initial success, then they can do more things. So people in TIFR, in SINP, so these are one of the locations where people are working actively in this India-based neutrino observatory. It is something very unique. And if in the next few years we can see something that is going to be a remarkable, and that is also going to be a remarkable success for us, because then we can actually contribute something fundamentally in this field, which is very challenging and evolving around the world. To finish the story, I must also mention about the dark matter. I'm not going into detail anything. Schematic dark matter detections are classified in 3 different ways. Of course, here I am typically focused about the WIMP-like object. So this is a cartoon diagram, which is extremely important. So if you have dark matter collision and some unknown interaction, because dark matter, as you see, is not a part of the standard model. So the way a dark matter can produce or interact with the dark matter with the standard model particle, it must be a BSM physics. So dark matter collision and giving you standard model particle. This is exactly, so this diagram, cartoon diagram which I've shown below, extremely important. This is precisely what has happened in the early universe when you have a lot of dark matter. But they started collided and they started producing standard model particles. And this is the mechanism known as ID, or indirect detection experiment. And here at the end of the day, as I showed in this diagram, you are going to get photon, neutrinos, and antimatter flux, mainly positron. You can detect them. There are experiments dedicated for them. Detect them and you have information about the dark matter. But later, and which is nowadays the main mechanism of detecting dark matter, because initially too many dark matter was there. So when they start, dark matter collision and giving standard model, so that is how their density actually goes down. Now the way we are trying to detect them, dark matter and standard model interaction. This is precisely something known as the direct detection experiment. Dark matter is coming from all across the globe. You place some nucleus, heavy nucleus typically, like xenon, one good example. They come, they interact, scattering, they goes away, but they deposit their energy in this nucleus. We detect the recoil and we measure, have information about the dark matter. And that is why you see that there exists a limitation of this experiment. If your dark matter is too light, so it is like so just think about this situation. So suppose you have an iron ball, say of the order of this football. You put it here. So this is like this is like the representative candidate which is representing your nucleus, and you try to hit it with a ping pong ball. what will happen? Nothing. Even if you fire like 10 or 20 ping pong ball at a time. So that means direct detection experiment cannot detect if the dark matter mass is too low. On the contrary, suppose you have a ping pong ball, which is now the representative of your nucleus, and you actually throw a cannonball at it. What will happen? The ping pong ball will go away. So also, if the dark matter is very heavy, then the recoil will be so large, it will be very difficult to detect. This particular window is something why we are actually putting so much emphasis about the direct detection, because this is typically the window of the weakly interacting massive particle, as I have shown on this detection graph. And finally, the last one, which we are trying to do at the LHC, it is the standard model particle which are colliding and they are producing the dark matter particle. As I have already discussed, so this is something that we plan to detect using this missing transverse energy momentum measurement, and that is how we plan to detect the dark matter. As of now, we have some limit, but no discovery. So that is the end of my talk. So thank you all for your patience and for your attention. I'm sorry I took a few minutes more because I just planned to finish everything by today.
It's all right. So we have finished with this lecture. So there are a few questions. You can also see in your chat box. One is, can you please suggest some elementary book on dark matter concept? Hello. Hello.
Any questions? Hello.
Can you hear me?
Can you hear? No problem.
Can you hear me? Hello.
Any questions? Hello.
Can you hear? Can you hear us? Hello. Hello. Can you hear us?
ভলিউমটা বাড়াতে হবে।
Am I audible?
Yes,
you are audible. Yes.
Hello.
You are.
Hello.
You are audible. Can you hear us?
I mean, unfortunately, I'm trying, but I can't hear you. Just 1 minute. Yeah. Could you please say something, Jaideep?
Yeah. Can you hear me?
Yeah.
Can you hear me now?
Could you please say it again?
Can you hear us? Hello.
Hello. Yeah.
Can you hear us?
Just give me 1 minute. Yeah. Could you please say hello?
Hello.
Yes, can you hear?
Yeah. Now it is better. So there was some problem with this.
Yeah, there was some problem. So you have 2 or 3 questions in the chat box.
Yeah. So first of all, I mean, so there is one question from Tiash. It's about the elementary book. Unfortunately, I don't believe there exists any elementary book in the dark matter. So if you go through any standard particle physics book, so most of them, they actually discuss something about the dark matter. And if you want to know about the basics of the dark matter and the calculation, there is a very nice paper written, I think around 1989 or so, by Gelmini and others. So that paper you can actually take a look, but I believe that you need to have certain amount of background for that. Anyway, I can give you some nice place. So for example, if you search about this. If you search in the internet, Ian Mambrini, so I mean, one of my postdoc mentors. So Ian wrote, so there you can see there is one book which is available for free for the dark matter. So that book is not complete, but that is probably the most detailed book I have ever seen. So whenever Ian is having something, he is just writing it down. So it is very detailed and very uh, like you can see a lot of information there. So that is freely available. So you can take a book, you can take a look. But otherwise, there is no very standard book which is of your level as of now. There are one book by Stefano Profumo about the dark matter. That is also a very nice book. You can also take a look. So then the question is about dark matter doesn't absorb radiation. How do we detect? So as I mentioned, so I really have no idea about the dark matter expansion. But regarding the dark matter, as I said, that they can, so this interaction, whatever way they are going to interact, this must be something beyond the standard model. So you cannot actually explain that with this electromagnetic strong or weak interaction. But there is a, so basically what you can think that if you want to embed dark matter in your theory, there must be some new kind of interaction. So for example, introducing some new gauge bosons like the Z prime or W prime. So this Z prime can act as a very good mediator for the standard mode, for the dark matter. So it depends on the theory. There is no uniquely defined actually object. So those are new interactions. So for example, just one very easy example is there. You have your standard model Higgs, so you can actually think about adding one more Higgs or one more scalar particle in the standard model. So that new particle, which is completely singlet with respect to standard model symmetry, you can think about this as a dark matter, and still you can write down an interaction with the standard model Higgs, and that can actually act as a standard matter. So this question I have already answered. So if you are not there, so existing phase, why it doesn't get heated up by sun rays? This is something that I have already mentioned. So regarding your standard model, this dark matter candidate, I can give you one example. So let me see for that. If you all can see my screen again. So so I just have one question to Jaideep and Shushabon. So
Yes.
I already have my like
You stopped your
tabs.
screen sharing, I think.
No, I stopped my screen sharing, but what is not clear to me that, I mean, I'm trying to share my screen and I'm just planning to use my own tab, but why it is not appearing here?
No, so you have connected your tab with your desktop.
Yeah. So yeah, exactly.
No,
So that is
I think it may not work. You have to then log in with your tab and then do the thing.
no, but actually it was logged in from the very beginning. I don't know. So anyway,
Yeah,
so
now it's coming. Now it's
no,
coming.
but
You
it
have some screen,
yeah,
but it's blank.
no. Yeah, but it is not but it is the default voice screen. So
Okay.
somehow in the Zoom, okay. But anyway,
Yeah, there are some problems maybe.
yeah. So just 1 minute. Let me just, maybe I'm taking a few minutes more because I'm not very confident here. So where is this pen? So do you have any pen here or nothing?
if you have some pen or something, you can write down on the screen.
No, is it? No, but it is not giving me any screen now. So it is not kind of touch screen kind of things. So maybe I just get rid of this idea. Let me see. Just 1 minute.
Mhm.
Okay, I'm sorry. So it seems that Zoom doesn't detect the external device. Okay, anyway, so
Maybe,
phi
but
dagger
you can say, yeah.
Yeah. So phi dagger phi, as I wrote with this mu square term, so that it doesn't matter whatever symmetry phi is carrying. Phi dagger phi is always invariant under any symmetry. So with that, just like this lambda phi 4 term, so which were like lambda phi dagger phi square, you can think about a term lambda phi dagger or lambda prime phi dagger phi times s star s, where s is a real scalar or maybe a complex scalar. If it's a real scalar, it will be s square. If it's a complex scalar, it will be s star s. This is a possible dark matter candidate. And then you can actually have process like SS going to 2 Higgs. So this is actually one dark matter possibility. And since Higgs field, you can actually expand after this spontaneous symmetry breaking and this thing. So you can also get diagram like SS meeting at a point, then Higgs, and the Higgs is decaying into a standard model formula. So this is how you can, using the concept of a scalar dark matter, to study everything. Unfortunately, this is a very simple model, and this is really, really constrained. So this is how dark matter is actually interacting. But you need new interaction mechanism. So I just gave you a simple example. This interaction. So what is this lambda prime? This is neither electromagnetic. This is neither weak. This is what? This is a new kind of interaction. Now, what is the origin of that thing? For that, you may actually extend your model, and you can have some new symmetry, and you can have a new force mediator and force carrier. So it is not confirmed. What is that? So that is the reason why there exists a plethora of model to study the dark matter. For example, in the context of supersymmetry, the lightest supersymmetric particle, it is considered to be stable. There exists some mechanism for that. And because it is stable, so we would expect that this can act like a whole dark matter candidate. So that's all. Okay, so one question is that if dark matter is invisible, how do you know its data? So for that, there are certain, observation. Even if dark matters are there and invisible, but like there are the dark matter, if it is there, so I would expect them to be very massive. There are certain dark matter which are very, very massive. So then there are certain, glitches in some cosmological and astronomical observation. So that actually gives you this idea that it is there. Dark matter is invisible. That doesn't, so it means that it is not interacting with light, but there are other way of interacting. For example, at the LHC, as I mentioned, that if you see two standard model particles are colliding and giving you something which leaves no trace, no charge track, nothing, no energy deposition in the electromagnetic calorimeter or electronic calorimeter, but just you calculate an abnormal large amount of missing transverse energy. So this is a possible signature of the dark matter. Of course, it is not guaranteed that this is the only possible signature of the dark matter. This can also happen from other stable massive particles. For example, if there is a massive particle which say decays after 20 meters, then of course LHC is not going to detect it. So it is not that kind of detection is not very unambiguous, but it's a possibility.
Okay, I think we don't have any more questions. And there is one question. Is there any properties of dark matter? I think they are thinking of dark matter as some electrons or protons, something like this. And that's why the problem is.
Yeah. No, see, everything, I mean, for example, what do you mean by properties? So properties means like mass. Of course, it has mass. Now, if it is stable, then we would expect it to have no charge, because that is how it can escape detection. But to give you these things, I don't know how much is your level of understanding, but there exists some literature where people have studied dark matter with tiny electric charge. So there are articles like that. But for that, you really need to know, certain other things about the dark matter. Spin of the dark matter also is something interesting. So that is why when they are studying this kind of interaction, there are things like spin independent or spin dependent called SI or ST interaction. That actually helps us to study the spin of the dark matter. So there are, quantities like which you can use to, define a dark matter. But I really don't know what is the level of understanding. So unless you have this elementary idea, it is rather difficult. And that also, this determination also requires proper knowledge about how a dark matter is coming and interacting with the particular nucleus. So if it is have some unpaired spin, that can give you information about the spin dependent cross section. If it is like a kind of a spin neutral object, like there is no unpaired nucleus in the outermost shell, then it is not going to give you any kind of information. So you will have a spin dependent measurement. And also dark matter properties is really sensitive to the mass. So as I said, right-handed neutrino, of course, we haven't discovered a right-handed neutrino, but that may act as a valid candidate for the cold dark matter if it is very massive. So properties means like it's a lepton, it has 0 electric charge, and kind of it has a certain mass, and it may appear with a certain chirality. So these are the kind of properties. It's a spin half object. So it may be anything. I mean, a dark matter may be a scalar, maybe a vector, maybe a fermion, everything. Because as of now, we haven't discovered any dark matter. So these are like different hypotheses.
Okay, I think we don't have any more questions. So I think, Ewan sir, are you there? For the vote of thanks?
Yes.
Yeah. So please carry on.
So, on behalf of the Department of Physics, let me thank the speaker, Dr. Pradipta Ghosh. Okay, we are really fascinated with the 3 days long journey. At a stretch, the lecture ranging for 2 hours, okay, and then lecture session, question answer session. Today, I think we have crossed 2.5 hours, and we are really very happy to see you, sir, to give this lecture starting from the road to the standard model and beyond. And today's part is really interesting in the sense it directly deals with the experiment. I thought with the theoretical research, the experimental update you have is really demanding, challenging. It is envious to us. You have cited the experimental result up to 2020. I should say to the students only, just see, being a theoretician, just to match with the theoretical results, how to have the experimental results as well at hand, and to grasp its meaning. It's really beautiful. So how to detect photon, it's a quite new idea to me. I'm indebted to you, sir, just to know the process for the detection of proton, electrons, okay, hadrons, okay, and the various parameters regarding the sensitivity, the resolutions of detectors, detection of neutrinos, and the recent investigations about the detection of dark matter. The students are very much interested to this particular point, and also the INO project in India. So we got a flavor of this particular physics, though I am not a expert of this field, not an expert. I have not studied it in details. Being a condensed matter physicist, I do some experiment on that. But still, during the 3 days, I learned a lot. I think students are also benefited. So being to give you at the vote of thanks, sir, I request you to come again and to deliver lectures to this department. And I congratulate my dear colleagues who have contacted with you. And for the beginning lecture, first day, we got our principal ma'am, vice principal sir, IQAC coordinator. I congratulate them all, and also they have provided, the college has provided us the Zoom platform for carrying out this lecture. For this, we are indebted, the Department of Physics is indebted to the whole college, and we are thankful to the other colleagues, and above all, the students who have shown their patience of hearing this beautiful lecture delivered by Professor Pradipta Ghosh. I am thankful to you, my dear students. And again, finally, thank you, sir. And when our teachers, your friends rather, will invite you,
Yes.
please come and join. Please come and join to us. Thank you.
Thank you very much, Professor.
Okay.
Thank
Thank you so much.
Thank you. So I think
So
we
it
can
was
stop here.
also, just 1 minute, Jadip. So it was
Yeah,
really
yeah,
a
sure,
nice
sure.
discussion. In fact, I mean, indeed, apart from like Jadip is the kind of my friends for several years, also like this college is very special to me, because so when I was actually in Kolkata and I was teaching in Vidyasagar, so in that time, it is the college from where I have received the invitation to being an external expert. So I remember to spend some hours in the lab.
Yes.
Doing this thing. Exactly. So it is always very special to me, and especially with Jadip, I share a kind of bonding for starting from my master's, because he was just my 1 year junior, and then we did our PhD together, staying in the same room, several things. So it's really a special. And also other like Shushovan, I also know from other sources, and Pradipta was my senior in science college. So it's a kind of, I mean, I would like to come again just to end in this thing. So it's also my thanks to all the esteemed faculty colleagues of the department, and to the principal ma'am, to the vice principal sir, and all the IQAC members for this opportunity. Special thanks to the HOD ma'am for this invitation. And just to end the story, I can see there is one more question, just to give you these things, a very quick answer. So what I just mentioned. So this 5 dagger 5 s square. So when the Higgs is getting a wave, so you are also going to get an interaction like Higgs going into a pair of dark matter. So this is possible. If there exists interaction, a standard model particle can also detect into dark matter. So this is possible. Sure, Shomadip, to answer your question.
So you can see the intensity of the lecture. After vote of thanks, you are getting more questions.
Yeah. Yeah. Dark energy, it has a non-particle origin, so I will not discuss about it. And
Yes.
thank you all the
Thank
students.
you.
for
Thank you also.
Thank you so much.
Thank you.
So okay, we can stop here, right?
We can stop.
Thank you all.
Thank you.